Wait, no spoilers for Palpatine. That's Return of the Jedi. If you haven't seen a movie from 1985, I'm sorry. Or whatever, 1980 what? Not 83. Okay, so yeah, witness the firepower of the fully electromagnetic boundary conditions. So first of all, what were the boundary conditions? Let's not go and write them all the way out. Let's share this application window. All right, so this is recorded. Oh man, that's blurry. I don't know. Can I make it bigger? Less blurry? Anyways, we see that we've got boundary conditions. That doesn't change it really. It's actually making it sharper for me when I expand this window here. There we go. All right, so we have these with we've got the field perpendicular to the interface, the electric field perpendicular to the interface, that's boundary condition 1. We've got the magnetic field perpendicular to the interface, that's boundary condition 2. We've got the electric field components parallel to the interface, and the magnetic field components parallel to the interface. So you don't have to remember these at all. I am going to refer back to them, and I'll just say, hey, look, we're going to go through boundary condition 1, 2, 3, and 4. We know that they're there. You know, I would have written them up normally on the board in a manner where they're like off to the side, and we can refer to them. Let's just refer to them in our minds without necessarily doing much with them. So I'm going to take this and stop that one. Go back to the whiteboard right here. Cool. All right, and so we said, okay, for our let me share another thing from last class, just again as a setup. Not quite. Bye, Jake. Come back, Jake. Here, I should have left it sharing. This bit right here, right? So, we have the wave coming from the lower left, right, is incident and bouncing off the interface, which is that vertical line, and reflecting, heading up to the upper left, and also another part of it being transmitted, heading up to the upper right there. And so if we call the normal, the z-axis, like we have been all along, with z equals 0 being the interface, then we know that they all lie within one plane. So let's call that the xz plane. Just we're free to choose that, but we might as well not mix together x and y. Just call that the x plane. We know that the electric field has to be perpendicular to the wave vector, so it can be anywhere in a plane perpendicular to those. Because we have the special plane already, the plane of incidence, let's just talk about the polarization vector being parallel to the plane or perpendicular to the plane, right? And we can also, of course, create any linear combination of those, but we can break those two down. And we're going to see that the dividing it that way produces a very nice way to organize it. Notice, so what we're going to do here is we're going to look at one of those two cases, and then in your homework you're going to look at the other case. So we're going to look at the situation where it's polarized parallel to the plane of incidence. And so if you take a look at that, for the electric field vector on the incident wave, that's again the one coming in from the lower left, notice that has components in x and z. And the same thing, the reflected wave, the electric field has components in x and z, and the transmitted wave, the electric field has components in x and z. For all three of those waves, though, there's no y component, nothing coming up out of the plane, because we've actually specifically chosen this case where there's no electric field pointing out of the screen. On the other hand, our magnetic field is entirely pointing out of the screen, because that's the only direction that's orthogonal to both the wave vector and the electric field. So that right there will will tell us which boundary conditions we can already start to apply, right? We don't have to worry about the y component of the electric field because the case we're looking at doesn't have one, so that boundary condition will tell us nothing. But we only have to look at the y component of the magnetic field because that's the only component there is. Okay, setup. We're looking at the case of electromagnetic wave that is polarized parallel to the plane of incidence hitting the interface. So what we're gonna do now is start applying our boundary conditions, the 4 that we looked at. So let's go back to this. Okay. To move around, get better access to this tablet. Switch. All right, cool. So again, and so that happens to be called P polarization, as opposed to S, standing for, and P stands for the German word parallel, and S is like Senkrecht or something like that, which stands for perpendicular, which means perpendicular. All right, so anyways, what are we going to do? We're going to apply our boundary conditions. BC for boundary conditions. So the very first boundary condition of those 4, right, had to do with the electric field perpendicular. We're doing this in advanced lab. Yes, we're going to come up to a version of the equations that we did in advanced lab, right? When we talked about, Professor Adler spent a whole bunch of time on kind of the microscopic view, which kind of assumes some of the stuff that we're going to just like peek at really, really quickly in chapter 11. What we're going to do is we're just doing this, assuming our media are just like they're just media. We're not talking about individual atoms or anything like that. We'll pause and do that. But so this is a different view, but it's going to result in the same equations or equivalent equations, a little bit different versions of them. Yeah, but this will be. So for those of you who haven't taken advanced lab yet, well, I was going to say, I'm like, for those of you who aren't currently in advanced lab, what you know. We've got a witness here that we actually talk about this stuff in other places in E&M class. Yeah, it's the basis of all kinds of technology. I'm hoping we don't have to do the experiment like we're doing today. I mean, currently in advanced lab next year, if you haven't taken it, because I am really hoping that we're back in person. So we have to take a look at the incident wave, and here we're going to write this in terms of its components. So we're looking at the Z component, and remember, here I'll draw over what this looks at like. That's our interface. Here is the wave coming in, the wave going out. Here's my incident wave, my reflected wave, my, whoops, kind of like that, transmitted wave, and there's my normal. So here's the angle of incidence, there's the angle of reflection, there's the angle of transmission. And so this is the x-axis, that's the z-axis. We're talking about the perpendicular component, the z, I'm sorry, we're talking about the parallel component. Oh, I know why. Right. So this is for our k vectors, right? And so if I were to take a look right here, this component right here, we could get this from taking our k vector times the sine of the angle. But we're looking at the electric field vector, and the electric field vector is at perpendicular to this. So if that's theta incident, then this right here is theta incident. So the z component is going to involve taking the magnitude here times the sine of the angle. And then we also had, oh, and notice right here, right? Why did I put a minus sign out front? Well, for this incident wave right here, right? If I had the electric field like this, so that the B, when B points out of the screen, then E cross B gives us the K vector pointing in the correct direction if I have it oriented like this. But then notice that the Z component of this electric field is negative, right? This electric field is pointing slightly to the left. Whereas up here, right, E cross B, to get it going the right way, this is going to be our electric field. So we'll have a plus E naught R tilde times, again, sine of the angle of reflection like that. And then over here, permittivity of material 2, and then here, again, E cross B to get it right. This is our electric field that's transmitted like that, and the magnetic field's coming back up. And so why am I choosing electric field that way? Like, I'm choosing my magnetic field to be pointing up out of the screen, and so that determines the direction of the electric field in order to have E 1 over mu naught E cross B giving us our pointing vector that points in the same direction as our wave vector, the direction of propagation. So here we notice that transmitted electric field also pointing off to the left. So that's why I have that minus E naught transmitted. Right, and these are just the complex amplitudes, right? Because we're taking the Z components of the vector. So it's not the complex vector. It's just complex amplitude times the sine of the angle. All right, so great. So what? Well, so now we have a relationship between the amplitudes and the properties of the material and the angle of incidence in transmission and reflection. So we've got a relationship. So that's one piece of information. So then, okay, so we got one piece of information. We'll come back and use that at some other later point. We can look at boundary condition 2, right, which had to do, which was about B sub Z, right? But B is entirely along the y-hat direction. So it's got no info from boundary condition 2. Right? B is pointing up out of the screen, so something about the Z component of it doesn't tell us anything, right? It's basically 0 equals 0. Yay, nothing there. Look at our third boundary condition, which had to do with the X and the Y components. Let's do the X components, right? So this is X components of the electric field, right? So here, the X component, well, so if the Z component was given by the amplitude times the sine of the angle, well, not sine, this is going to be times cosine. Right? And once again, we can take a look and we can see, well, in all cases, their point is pointing upwards. I mean, sorry, yeah, upwards in the picture. So that's positive X. So these are all just going to be cosine with positive sign. So now we've got another set of relationships between these amplitudes and the angles. Right? And eventually what we're going to do is combine them to come up with something that makes a little more sense. All right. Okay, and then there's nothing about there's no information from the Y components boundary condition because we're looking only at electric fields that have no Y component. All right, so then we can move on to the fourth boundary condition, and which was about the parallel components of B. So no info from the X components because we only have Y components. And before we do stuff with the Y components of B, though, let's remember that B naught, the amplitude of B is 1 over the speed in the material times the amplitude of the electric field. So now we had 1 over mu1, whoops, running off the edge of the pad, 1 over mu1, and then I'm actually going to bring in the V so that I can write this in terms of my electric field amplitudes now too. It was 1 over mu1 times V1, but we're going to write it in terms of just our electric fields. So we got that. And here's an E naught incident tilde. And then we're actually going to have the same prefactor of 1 over mu1 and 1 over V1. So I'm just going to factor that out. And we'll have the E naught reflected, right? And notice that they are pointing opposite directions. I'm sorry, our B's are pointing the same direction, but we had a minus sign between them, and so we got these. Okay, great. So let's do a few things here. One of the things is, yes. Yeah, how do we get this minus sign between them? Let me try to remember this. I just suddenly got confused about that too. Give me one moment to flip back at something here. Is plus sign. I don't know off the top of my head. I would have to look into that. I can get back to you about it. We could also look into the textbook because it talks about some of this, but I wanted to make sure we had a different way to explain a bunch of what's going on with a little bit more details. Rather than tracking it down, I'd like to keep pushing forward, but yeah, just accept that I'm not doing a good job of keeping track of where that came from. So my apologies for now, but let's hold off on that for now, just so we can get to the big picture stuff. Okay. Yeah. So my recommendation is in some ways is to go back and forth between the textbook and your notes or lecture. It'd probably be easiest just to follow, the textbook has it right in front of you and you can kind of like hop around more easily in terms of what you're going to be mimicking for the other case. But then if you don't understand some of the steps, you can refer to the lecture notes for that. So hopefully the clarification will be in the textbook, but I will also try to track that down later on. Okay. So I want to leave a little bit of this up here. I'm going to try to work in the remaining space in the lower right without getting too cramped. So we're going to use these things right here, like that. So the first thing is we can simplify these things a little bit, right? We can say that we know that from the law of reflection that the angle of incidence is equal to the angle of reflection. So we can substitute that in for, we can rewrite 1. Well, the consequence of boundary condition 1 right there. So we've got epsilon 1. And what I'm going to do is multiply through by an overall minus sign. So we'll do E naught I tilde, and I'm going to make this one a plus, and then that makes this one a minus sign, E naught R tilde, and then I factored out a common factor of sine of the angle of incidence, because one of them was sine of angle of incidence, the other term was sine of angle of reflection, but it's the same, the angle is the same magnitude, right? And sine. And then over here, right, we've got plus E2, because I've multiplied by a minus sign, E naught T tilde time, I'm sorry, sine of theta T. I'm sorry, but that. So let's see, we can do a few other things. We are going to write some things down. We wrote down before. We can now, let's get rid of the angle of transmission, right? We had before that the sine of the angle of transmission divided by sine of the angle of incidence, and we wrote it a couple different ways. One way though is n1 over n2. So this is coming from our law of refraction, which is v2 over v1, right? So let's rewrite this using that, coming down this way. Oh, I'm sorry. That is going to be this right here. So I'm going to divide through by that epsilon 1, and my sign also. Right, so we've got that, but then I can rewrite that right here as epsilon 2 over epsilon 1, and this is going to be n1 over n2. And we've got this amplitude here. Right. So we've got the difference in the incident and reflected complex amplitudes is proportional to, with a particular constant proportionality, E naught T, like that. But we can actually say something about these indices of refraction too. So just remember, N is equal to C over V. Another way to write that is C is 1 over mu naught epsilon naught square rooted, and V is 1 over mu epsilon square root. So because in the denominator we get mu epsilon in the numerator, and then still divided mu naught epsilon naught, like that, right? And so over here, where we've got this ratio of the indices of refraction, right? Obviously, the mu naught epsilon naughts will cancel out in this ratio. And so this becomes the ratio of the square root of mu1 epsilon 1 divided by the square root of mu2 epsilon 2. Right, so let's just go back and write this again. So we've got I don't mean to be slanting like this. Sorry. So here we can write this then is, we cancel out the square root of epsilon parts, and we've got square root epsilon 2 over square root epsilon 1, and then square root mu 1 over square root mu 2, right? And then I can let's take that and multiply through by mu 2 over mu 1. I'm going somewhere with this, I promise. Mu 2 over mu 1. And so then we're going to be left with mu 2 wait, do that. Sorry, let me just erase all that. I know what I'm trying to do, but that didn't make sense what I just said. All right, and so I can write this right here as same thing. Oh, I'm going to write this. We've got an extra mu1 right here, extra mu2 here. This is square root of epsilon 2 mu2 over square root epsilon 1 mu1, and I've run out of space. So let's take a snapshot of this, and I'm going to finish it up, and it's going somewhere, believe it or not, right? So that was poorly handled space-wise. Let me just save this for you, and we'll finish this up. Give me 1 second. I can't see that. Comment was, where did the factor of mu1, mu2 come from? So that is already there right here. What I did is I pulled out, I noticed that if I take this right here, if I want to have, this is the same as having the square root of mu1 in the numerator is the same as having mu1 times square root of, divided by square root of mu1 right there. And so, same thing right here. So why am I doing that? It's partly a question of why, right? You can see that this works out. It's what I'm trying to do is head somewhere where we've got the properties of the materials laid out in a really compact form, and part of it depends on a ratio of the mu's, and the mu's are often the same, and so that ratio then becomes 1. All right, so let's keep going with this on a new board, and my apologies for just barely running out of this, right? So we were looking at the difference in the complex amplitudes, and we'd gotten them to the point where this right here was equal to, we had mu1 divided by mu2 times the square root of mu2 epsilon 2 and the square root of u1 epsilon 1, like that, right? And then, hey, look, is actually the same as having that mu1, mu2 times, look, this is actually proportional to the index of refraction, and that's proportional to the index of refraction. Or another way to write this is mu1, mu2, and this would be v1 over v2, like that. So it's convenient. Part of the reason why we're doing this is so that we can write it as a nice compact. Oh, and I kept dropping something. I think I dropped this repeatedly, the fact that there's the transmitted amplitude here times the transmitted amplitude times the transmitted amplitude. Again, my sloppiness. But now we've got this written as just a simple ratio of properties of the materials. So this difference of the incident and reflected amplitude is equal to the transmitted amplitude times ratio of these properties of the materials. And what's more, a lot of the times mu1, mu2 are equal to mu naught, and so that that part of this ratio, mu1 to mu2, just becomes 1. So nice, simple way to relate these things. All right. So we simplified this. We're going to come back to this. So hold for later. All right, so let's turn this pad so when I write, I don't slant downwards. Let's take that, and if we were looking at, so let's rewrite this right here then, actually. So let's call this ratio right here. Let's call that ratio there, or this ratio right here. That's really poor job circling. My apologies. We're going to see things using that a lot, so we're going to call that ratio beta. Or another way to say that, mu1 and 2. Like that, right? So again, hold on to that. So another way to say this is now, actually, what we're not going to hold for later, what we're going to have is E naught incident minus E naught reflected is just equal to beta times E naught transmitted. So here, forget about holding that one. Let's hold this one for later, right? So that really ugly looking thing with epsilons and sines and cosines and stuff like that is simplified down to just kind of this linear equation right here. And so that came from number one, from 3, right? We do all that. We go through a similar process. Let's not do it all. Let's just say, hey, we go through it and we get E naught incident. That was plus E naught reflected. Right? And this was the one where we had the cosines times each of these things. But what I'm doing is going to move, we had cosine of the incident angle and cosine of the reflected angle, but those are the same thing. So I factored out that cosine and divided it through on the other side. And so now alpha, right, and this was here. This was actually a definition. So I'm going to define alpha, right? That is just going to be the ratio of the cosine of the transmitted wave divided by the cosine of the incident one, because we were able to factor that out because the reflected angle and the incident angle are the same thing, right? So now, right, we've got these two relatively simple equations, right? It's a system of equations, right? And so that right there, this defines our relationships between our fields. It's not necessarily the most useful format, because usually what happens is we know the field that we're sending in and the angle, and then we want to see what comes out as reflected and transmitted waves. And so let's express the reflected amplitude purely in terms of the incident angle and incident amplitude, and same thing for the transmitted one. So again, just do algebra. And alpha and beta. Alpha has to do with the angle that we send it in, and properties of the material, and beta has to do with just properties of the material. So we do that, and you get this relationship. which is relatively straightforward. And the transmitted amplitude is also relatively straightforward. We had to do a bunch of work to get to this, but that's not too bad. And so this is our result right here. We'll see what it means and we'll do other stuff with it, but this is the result of all that work, right? And we have to look up above to what beta is right here, right? Remember, this is beta right here, and that's alpha right there, right? And this specifically is Fresnel. So it's not, is here, let me type it out. Okay, so these are called Fresnel, not Fresnel. Fresnel, again, another French name. Fresnel's equations for polars, and we were doing specifically the case of polarization parallel to the plane of incidence. And again, that for historical reasons is called p-polarization. Right? So let's take a look at what these things actually mean. What are the implications of Fresnel's equations here? So first thing, our transmitted wave. So on the right-hand side of that box there, right, it's going to be, we've got alpha and beta, which are real numbers. 2, that's a real number, times our complex amplitude. So, and all those, alpha and beta, positive, right? So 2 over positive numbers, positive real numbers. So first thing is our transmitted wave is always in phase with the incident wave. Someone's pointing at the 2. Yes, that's what we're talking about right here. Right. So,
Wait, how is it 2?
yeah. So where the heck did the 2 come from? From both of those right there. What I did was I skipped over a whole bunch of algebra that combined the 2 red underlined equations. Right. Not a whole bunch, but like 3 or 4 or 5 lines of just moving things around to get to isolate E naught T. So right, I could multiply the second equation or divide this first equation by beta, divide the second one by alpha, add the 2 together, then combine some common denominators, and yeah, that's what we would get right here. And the E naught R's would cancel out. Or another way to do this actually would be to just add these 2 together so that my E naught R's drop out. And so we've got a sum of 2 equations in terms of E naught I, E naught T, and a bunch of coefficients. And then once you gather it all together, clean it up, you end up with this. But I didn't think you wanted to see me stumble through all of that. I thought it'd be more important just to see, hey, what are the equations? What are they in terms of the physics? Cool. And sorry, transmitted wave always in phase. Right, in or out of phase. So in phase is supposed to say same sign. out of phase is sign flipped. Right? Alpha minus beta over alpha plus beta can be plus or minus, right? So depending on both the properties of the material, basically the ratio of the indices of refraction and their mu's, and also the angle of incidence, we can get different different things going on with the reflected wave. So that's one set of information right here. Let's see. So another thing that we have right here is that both the reflected and transmitted waves, their amplitudes, they're complex amplitudes, right? So including phase. So they only depend on two things, right? The materials that are involved, specifically via mu, this is supposed to be an ampersand, and n, right? And the other thing that it depends on is the angle of incidence, right? How we strike the material. You might say, wait a second, right? Right? I get that in terms of beta. Beta only has mu and n, but look at alpha over here. Alpha's got the cosine of the angle of incidence, but also has the cosine of the angle of transmission too. So doesn't it depend on how the light gets transmitted too? And let's do a quick derivation to show, well, yeah, no, actually, the angle of transmission can be re-expressed in terms of the angle of incidence and the properties of the material, right? So specifically, right, we had beta, right, was just mu1 and 2 and mu2 and 2, right? Cool, that's the materials. Let's look at alpha. Alpha equals, we got cosine of this angle, right? And then cosine of the angle of incidence. So let's take a look at that cosine of the angle of transmission. I can take that and rewrite the cosine as, well, 1 minus sine squared, and then take the square root. Take the square root. And this is still cosine, angle of incidence. Oh, and wait, we've got something that relates, we've got the law of refraction that relates the sine of the angle of transmission. I can write this as that whole square root is going to be 1 minus, this is all going to be under the square root, but the sine of the angle of transmission is actually n1 over n2 times the sine of the angle of incidence. Angle of incidence, right? And that whole thing is playing the role of my sine of angle of transmission. So that group right there gets squared, and that was all under a square root. And that's still divided by cosine theta I. Right? So now this is only mu n and the angle of incidence, right? Like we said, it only depends on the properties of the materials, and the, so that's a comma, not a 1, right? So now we can see that, yeah, everything here only depends on on the angle of incidence, and then the mu's and n's, the ratios of them actually. Not too bad. All right, so let's see some other implications of all this right here. So let me quickly save this. Okay. So, just taking a look back at those, and so I'm really quickly going to write those again. So, oops, Fresnel's equations. So let's see, what do they actually tell us about what's going on? So we saw what they depended on. We saw what they tell us about the phases. Let's see, and in physics, what we do is we typically look at one limiting case, the opposite limiting case, and then see what happens in between. So one limiting case is normal incidence. So case. What about normal incidence? That means along the normal, right? The light comes in normal to the surface. So the angle of incidence as measured from the normal is 0, right? So we do that, and so then we get, right, alpha, which was going to be the ratio of those cosines, right? Alpha equals cosine theta t over cosine theta incidence. Well, if the angle of incidence is 0, that denominator is 1, and we actually know that the transmitted angle has to be 0 too from the law of refraction. Doesn't matter what n is, n1 and n2 are non-zero, and if the if the angle is 0, sine of 0 is 0, so then the other angle also has to be 0, so that we can get, according to the law of refraction. So then cosine of 0 becomes 1, so we get 1 over 1, like that, right? So then we can write, here, we'll write it down below. My reflected amplitude is 1 minus, because alpha is 1 minus beta over 1 plus beta times my incident amplitude. And we've got and we pause at this point and say, hey, that's what we saw 2 classes ago, right? We did the special case of normal incidence. So, well, that's kind of a relief. We went through all this work. It better reproduce what we've done before in that limiting case. So here, that's case A. Let's do case B. What's the other extreme we could have? Not normal incidence. Let's have theta equal 90 degrees. Right? So that's going to be a grazing incidence. So again, for this theta, so if this was the interface between the materials, right, this 90 degrees would be, sorry, normal incidence, 0 degrees would be the light coming in like this, right? And it's going to keep going through like that. So now what we're looking at in this case is a situation where, right, that's our interface. This is my normal. So 90 degrees from the normal, our wave is coming in basically and striking the material just like this. And I'm exaggerating. It really it's like totally skimming the surface. Right? And that angle right there is 90 degrees. All right, so we stick that in, and then in that case, the cosine of the angle of incidence is equal to 0, right? Um, so if we take a look at that, ooh, what's that? Where theta, yeah, sure. We can take the limit. The difference is, drawing the number line with the empty circle for the full circle. And in physics, like we can't actually define a single point, have like things going in exactly a single angle. So it's going to be a narrow range of angles. So yeah, sure. Um, all right, so we've got that right there. And so we've got this right here, and we also have our transmission cosine theta t. Doesn't have to be equal to 0, right? So let's see what happens to our alpha. So our alpha is cosine of the transmitted angle divided by 0. What? So that alpha is going to infinity. So yeah, well, I mean, maybe we should be taking a limit because this is going to infinity, and then we've got weird stuff going on right here. So let's see. E naught r tilde is equal to infinity times E naught incident, right? Which is equal to the, okay, so the reflected amplitude is equal to the incident amplitude. That seems kind of weird, like, because anything that gets transmitted inside is going to be extra amplitude then, and that would seem like we'd be creating more electric field, violating conservation of energy. Well, anyways, we got 2 over infinity plus beta is just infinity times E naught I. Oh, I see what's going on, right? We've got 2 over infinity is equal to 0 right there, right? No transmitted wave. Right? It's completely reflected. So actually, like wherever you are, if you've got some kind of surface, it doesn't have to be like a shiny surface like glass or metal. Even if you're near like a painted wall or a desk, or even like a boulder here, if you take and look right along it at a grazing incidence, you'll actually be able to see like a bit of an image, reflected image, a bit of color, and so on, right? You can do the same thing on a desk, much more so than if you're just looking down. You won't see looking straight at your desk surface or your binder surface or something like that. You won't see a reflection, only on something kind of like really smooth and nicely reflecting, like the surface of a piece of glass or something like that. But any surface, if you look at a grazing angle, you can get a lot of reflection, right? So cool. So, all right, we've got that right there. So let's take a look at the case in between these things right here. We can do this. Just grab the snapshot. Okay, so in between those two extremes, oh, and again, let me just really quickly write this. E not R tilde equals, right? There's another place where where that numerator can go to 0 when alpha is equal to beta, right? Whoops, no reflection right there, right? So alpha is equal to beta. So, right, we wrote down alpha. Let's see what that angle is. We wrote down alpha. Alpha equals beta. I'm going to write it this way. This is 1. We'd already figured out alpha was this thing right here. And 2 sine theta incident squared, all under the square root. Here's the cosine of this angle of incidence. And it's not just any angle. We're going to call this a special angle. So here, let's call this angle right here. We'll give it a name, but we're going to call it theta sub b. Right? This is our Brewster's angle, is to give the punchline. Right? So this isn't any old angle of incidence. This is the one where alpha equals beta, and we get 0 reflection. So that's equal to beta right here. Let's just keep working through this. So we've got 1 minus n1 over n2 sine theta b squared over 1 minus sine squared theta b. And this was under a square root. That's under a square root. That's equal to beta, right? So would you believe that we can isolate our theta b in all this right here? So here, math, algebra, right? And we could write this now as sine squared of Brewster's angle is equal to 1 minus beta squared. Again, not obvious, but just trust me for now that you can get there. Let's actually remember beta can be written in terms of my mu's and my index of refraction n. So let's simplify that. Most materials, right? We've got mu1 about equal to mu2, which is about equal to mu0, too. So in that case, going to be about equal to the ratio of just the indices of refraction, because the mu's are equal, so they just give us 1 in their ratio. So, all right, then our sine squared of Brewster's angle simplifies down, right? We've got 1 minus beta squared over this ratio. Well, that's 1 over beta squared. So I don't like having a fraction in the denominator. So let's multiply through by beta squared. And then, hey, we can factorize that. The denominator is actually the product of perfect squares. So I'm going to leave the numerator alone, 1 minus beta squared. I'm sorry, I put this, I've got a mistake with my parentheses right here. That's good. And then in the denominator, I can write this as 1 plus beta squared times 1 minus beta squared. Right? It's the difference of perfect squares. So I can write it like that. And so, oh, well, I can then simplify this as beta squared over 1 plus beta squared. Question, will beta ever equal 1? The only time beta will equal to 1 is if mu1 equals mu2 and n1 equals n2. And so that means you're going in a continuous serial. Yeah. Okay, I'm just about out of time. Let me just make the conclusion. Let me just conclude this in the next minute, and I apologize for going over. So we've got this right here. That's kind of an ugly thing. That tells us what this angle is, but we can simplify it. So let's take a look at cosine squared of Brewster's angle, right? Not 0 over 0. It would be 1, alpha over alpha. And so we'd be okay. So this is 1 minus, I'm going to square. That was sine squared, what we just gotten. So I'm going to write that in, 1 plus beta squared. And so this is 1 plus beta squared minus beta squared over 1 plus beta squared. And so that's going to be equal to 1 plus beta squared. 1 over 1 plus beta squared. So the nice thing now is, right, I've got from my, before I had beta squared over 1 plus beta squared, and here I've got 1 over 1 plus beta squared, so I could get rid of those denominators, take their ratio, right? And so the tangent squared of Brewster's angle, right, which is sine squared of Brewster's angle divided by cosine squared, right, which is equal to the beta squared over 1 plus. So here, tangent of Brewster's angle is equal to beta, which is about equal to n2 over n1, right? So another way to say this is theta Brewster is equal to the inverse tangent of n2 over n1. Right, so that's going to be useful. So this is the angle at which, oh gosh, this is the angle at which light polarized this way doesn't reflect. And what we're going to do is next class, we're going to play around with this, play around with polarization, and talk a little bit more about about other effects, what happens for various values of epsilon and beta for our different materials. What kind of behaviors can we see? So sorry again for running over. We'll take a look at the consequences of all of this in our next class before we start talking about absorption. Cool. Sorry, I got a little bit rushed. I got a little slow start. Cool. Yes, question?
Yeah, can I explain sort of what I was trying to get at with that comment?
Sure, yeah, and everyone else, you're welcome to hang around or to head out if you got other places to go, or virtually. Yeah, go ahead, Harry.
So if beta squared was 1, right?
Yes.
Then at this
There.
point,
Yeah.
we get a 0/0 case, don't we?
Right. And so remember this was yeah. And so is that a problem, a 0/0? It it's not a problem unless it could be a problem or it could not be a problem. You have to take a look. Basically at that point you better double check your physics. And so what that why is it um 0/0? Well, we're saying there's going to be no reflection. It's going to be um, if beta is equal to 1, that means you're basically got no interface. It's all just one continuous material. And we're saying there's no reflection at this special angle. But I think what you're going to find is if beta is equal to 1, right, that's actually going to save us, because otherwise it's it would give us a specific angle at which there's no reflection, or still, right? Because if we exclude the
Okay.
if we don't say, hey, there's a problem here, we would get 1 squared is equal to 1 plus 1 squared. So we would get on the for the ratio 1 squared over 1 plus 1 squared, so it would be 1/2. So theta Brewster would be equal to whatever angle has arc sine of square root of 1/2, so that's going to be 45 degrees. But it turns out actually any angle you send it, there's going to be no reflection, right? So that's where the 0/0, you're like, hey, wait, it's not just anything, that one angle. Any angle is going to give us this result, and that it's because of that 0/0.
Okay.
No.
That makes sense. Thank you, Dr.
Yeah,
Grossman.
yeah. So anytime you've got the like divide by 0, is it when there's a 0/0, usually we can escape it, but it does mean like check what's going on, and there's usually something weird that you either can ignore from physics or say, well, this is everything because of physics.
Okay.
Cool.
Awesome.
But
Have
yeah,
a good weekend.
yeah, you too. Take care.